In earlier lectures, I reviewed the gas laws. I explained that these gas laws or gas equations work nicely to explain and predict gas behavior mathematically. But these equations only give us a quantitative view of gas behavior. What these gas laws don't tell us is why. Why do these gases behave the way they do? What is an ideal gas? And what is ideal behavior? For this, we have what Atkins and De Paula call one of the most remarkable and arguably most beautiful models in physical chemistry. For from a set of slender assumptions, powerful quantitative conclusions can be deduced. This is the Kinetic Molecular Theory. Let's start with a visualization of solids, liquids, and gases. First, solids have particles in closed, fixed positions. And when solids melt into liquids, these particles have more positions available to be in. Notice, in the liquid phase, these particles are more spread out, but still close to each other. But in the gas phase, these particles are allowed to occupy any position available, as per the rules of entropy or randomness. In fact, one can think of the gas phase as mostly empty space. Keep this in mind as we discuss kinetic molecular theory. Kinetic molecular theory states that the distances between particles is so great compared with the volume of the particles that we can essentially ignore the volume of the particles and ignore the interactions or forces between particles. This is important because this means we can treat the particles as individual entities, which is one of the reasons the gas laws work. Here are the first two postulates of the kinetic molecular theory. Since the gas phase is mostly empty space, we can treat particles as a point of mass and ignore the volume and assume the volume of each particle is negligible. Second, we can ignore the interparticle forces. At ideal temperatures and pressures, the gas phase is mostly empty space, and in the rare occurrence that these particles do collide, we can assume any collisions are elastic and brief. Here's the third postulate of kinetic molecular theory. Gas particles are in constant random motion. They must be. This is why they exert pressure. Balloons and tires stay inflated. When the particles collide with the walls of the container, they exert pressure. And finally, the Kelvin temperature of the gas is directly proportional to the average kinetic energy of the gas. This gives us the meaning of temperature. Thermodynamically speaking, the average kinetic energy is equal to 3/2 RT. Recall, the ideal gas law applies to all gases behaving ideally. Similarly, notice how the average kinetic energy of a gas applies to all gases behaving ideally. Kinetic energy is only dependent on the temperature of the gas. In our next video, let's discuss how we arrive at this equation. One of the interesting postulates of the kinetic molecular model is that it gives us the meaning of temperature. In thermodynamics, the kinetic energy of a collection of gas particles is equal to 3/2 RT. And you may be noticing something looks familiar. That's right. Recall the ideal gas law is PV equals nRT. If we set both sides of the equation equal to RT, we see that 2/3 kinetic energy is equal to PV over N. Let's discuss how we arrive to this elegant thermodynamic relationship. Consider a gas particle in a box. According to kinetic molecular theory, the gas particle is in constant motion, and from time to time it will collide with the wall of the container. And kinetic molecular theory assumes that these collisions are elastic. In other words, kinetic energy is conserved. More on this in a moment. Let's move our particle in a box over to the side and look at the pressure of a single gas particle. The pressure is the force per unit area. And from Newton's second law, force is mass times acceleration. And acceleration is the change in the velocity over the change in time. Let's focus on the change in velocity first. The particle is traveling with some initial velocity, then collides with the wall of the container. Since the collision is elastic, the final velocity is the same as the initial velocity, except with the opposite sign, since the particle is now traveling in the opposite direction. Thus, the change in the velocity is 2v. I'll insert 2v into the equation, and I'm using the absolute value, since the direction of the particle isn't important for this exercise. Now let's resolve the change in time. Kinetic molecular theory does something clever here to account for the change in time by multiplying the equation by the collisional frequency. This is how often the particle collides with the wall. The particle in the image is traveling with some velocity and will eventually collide with the wall of some length L. The collisional frequency is V over L. So let's multiply the collisional frequency and remove the change in time. Here's the updated equation. So far, we've considered one particle moving in one direction. But of course, it moves in three directions. So we'll assume the velocity term in the equation reflects all three directions. Now, we can look at the area term. This is relatively simple. The area would be one side of the box of length L squared. And of course, there are 6 sides of the box, so the area is equal to 6L squared. Let's insert this into the equation for area. 2 over 6 is 1/3, and the length terms multiply in the denominator to give length cubed. I'll multiply by n, the number of moles. Up until now, we were considering one particle. Now we'll consider a mole of particles. And finally, let's close our proof by multiplying the equation by 2 over 2. Yes, this sounds silly, but when I insert 2 over 2 into the equation, we see a familiar friend. 1/2 mv squared is kinetic energy. Let's rewrite the equation in terms of kinetic energy. I'll rearrange to solve for the kinetic energy. And recall from the ideal gas law that PV over N is equal to RT. We can substitute this term into the kinetic energy equation and get our final equation. This brings us back to the fourth postulate of the kinetic molecular theory. The average kinetic energy of a gas is directly proportional to the Kelvin temperature of the gas and equal to 3/2 RT. Notice how the kinetic energy of a gas is dependent only on the temperature. So this equation applies to all ideal gases. Next, let's use this equation to relate how the velocity of a gas is affected by its mass and temperature. We know that the kinetic energy of a particle is 1/2 mv squared. Let's set these equations equal to each other and solve for the velocity. The first thing we'll note are that the halves cancel. Next, divide both sides by the mass, and the mass will cancel on the left side. Note, I'll change the lowercase m for the mass into an uppercase M. This signifies that I'm referring to the molar mass of the gas in kilograms per mole. Finally, I'll take the square root of both sides and get the square root of the velocity squared. We conclude with the equation for what's called the root mean square velocity. Note that the symbol for velocity in thermodynamics is the Greek letter mu, and RMS stands for root mean square velocity. The big conclusions from this equation are that the velocity of a gas is proportional to the square root of the temperature of the gas. The higher the temperature of the gas, the higher its kinetic energy, and the higher its velocity. And the velocity is inversely proportional to the square root of the gas's molar mass. The heavier the mass of the gas, the slower its velocity. Now let's take a closer look at what exactly the root mean square velocity is. It's important to note that for a sample of gas particles, there's a distribution of velocities. Here is an example of a Maxwell-Boltzmann distribution of velocities, which plots the probability of a velocity versus the velocity. You can see that the peak is the highest probability velocity. But note, the distribution isn't symmetric. The average velocity is slightly to the right. And the root mean square velocity, mathematically, is even farther to the right of the average. The point being is that mathematically there are different ways to express an average velocity, and the root mean square is one of them. In the end, there is a less than 10% difference in the average velocity and the root mean square velocity. The most important point is understanding the general trends from the equation. For example, let's rank the following gases all at STP in order of smallest to highest velocities. Note, all of the gases are at STP. They have the same temperature, thus have the same kinetic energy. But their velocities are inversely dependent on their mass. The heavier the mass, the slower the velocity. Let's find the molar masses. Here are the molar masses for the gases. Chlorine is the heaviest, thus the slowest gas. Carbon dioxide has a lower molar mass than chlorine, thus slightly higher velocity. Next is oxygen, then neon. Finally, hydrogen gas, the lightest gas, has the highest velocity. There are two interesting phenomena that arise based on gas motion: diffusion and effusion. Imagine a container with two different gases separated by a divider. Then we remove the divider. The gases are in constant motion, thus will eventually, after some collisions, mix. This is called diffusion. Now imagine the container with a divider, but the gases are mixed in only one half of the container and the other half is a vacuum. If the barrier has a small slit, the gas particles will escape the chamber that they are in and go into the other chamber. This is called effusion. Diffusion is the mixing of gases, while effusion is the process where a gas escapes from one chamber to another through a small opening. Rate of effusion is the time for the gas to effuse, and usually reported in units of volume per unit time, like milliliters per minute, for example. And this is dependent on gas velocity. Recall, the root mean square velocity is the square root of 3RT over the molar mass of the gas. Here we see the root mean square velocity of two gases. Thomas Graham proposed a simple yet elegant equation to compare two gases under the same temperature and pressure conditions. Since the square root of 3RT is a constant, We can say that the effusions of two gases are inversely proportional to the square root of their molar masses. Here's the proportional relationship without the square root of 3RT. Simply take the ratio of both sides, and here's Graham's law. Notice how the rates are inversely proportional to the square root of the gas's molar mass. Now, if you know the rate and molar mass of some gas, you can compare rates to find the molar mass of an unknown gas. Let's do an example. A flammable gas made up only of carbon and hydrogen is found to effuse through a porous barrier with a rate of 1.50 milliliters per minute. Under the same conditions of temperature and pressure, it takes an equal volume of bromine vapor, a rate of 0.48 milliliters per minute, to effuse through the same barrier. Calculate the molar mass of the unknown gas and suggest what this gas might be. Because we're given effusion data of two gases, we can use Graham's law to compare the unknown gas to the known gas. It doesn't matter which gas is gas 1 or gas 2. I typically assign the unknown molar mass as the numerator. Therefore, bromine can be gas 1 and the unknown gas can be gas 2. The unknown rate will be in the denominator on the left side, and the bromine data goes here. Since I'm not using the gas law constant R, I can use units of grams per mole for the molar mass. The unknown is inside a square root, so we'll have to square both sides, then multiply the bromine mass to get the mass of the unknown by itself. Solving this gives us a molar mass of 16 grams per mole to two significant figures. Methane is the likely unknown since its molar mass is 16.05 grams per mole. Recall, kinetic molecular theory states for ideal gases, that is, gases at high temperatures and low pressures, or large volumes, we can essentially ignore the volume of the particles and the interactions or forces between them. For gases like this, we can use the ideal gas law. But what if we increase the pressure by decreasing the volume? Now there is less space for the particles to be in. And at lower temperatures, the particles have less kinetic energy, thus less velocity. They're moving slower. Now we can't ignore the particle volumes and interparticle forces. These are commonly referred to as real gases or non-ideal gases. We'll have to account for these factors when calculating the gas pressure. While a few equations have been proposed, van der Waals equation is most commonly used in general chemistry. Van der Waals equation attempts to find the observed pressure of a real gas. Notice how the equation is built off the ideal gas law, but with two obvious corrections. The minus NB term is called the volume correction, and the minus A N over V squared term is called the pressure correction. Let's discuss these corrections. Since the gas is now restricted to a smaller volume, the volume must be corrected, and this is dependent on the size of the particles. The particles are taking up space too. Next, the force of the collisions are reduced because of the attractive interparticle forces. This includes collisions with the wall of the container, thus less pressure. There needs to be a pressure correction. Let's return to van der Waals equation. A and B are called van der Waals coefficients for the volume and pressure corrections, respectively. Here are some coefficients for a few gases. I've chosen helium, neon, xenon, and water for this exercise. Helium and neon are small noble gases with small polarizabilities, therefore exhibit weak interparticle interactions. Their coefficients are very small compared with xenon and water. Xenon is a very large atom compared to helium and neon, and thus more polarizable. Therefore, xenon atoms interact strongly with each other. Water is a very polar molecule, thus exhibits strong intermolecular interactions. The coefficients for xenon and water are much larger. Let's compare the pressures from the ideal gas equation to van der Waals equation, and I'll start with the ideal gas equation. Let's find the pressure for 1 mole of 1 liter of each gas at 273.15 K. Of course, the ideal gas law will give the same pressure for all the gases, 22.4 atmospheres. This would be the same pressure for all gases if they behaved ideally. Now let's use van der Waals equation to find the pressure for helium first. The equation may look busy, but try to keep the equation organized by completing the calculation in parts. Start by finding the volume correction, then finding the uncorrected pressure, then subtracting the pressure correction. Interesting for helium, the pressure observed from the van der Waals equation is 22.9 atmospheres. Notice the ideal gas law pressure closely resembles the observed pressure. The van der Waals pressure for neon is 22.6 atmospheres. Interestingly, the ideal gas law gives a pressure to within a 2 and 1% error, respectively, for helium and neon. Now, let's look at the observed pressures for xenon and water. You can see the observed pressures from van der Waals equation of 19.4 and 17.6 atmospheres for xenon and water, respectively. These represent a 15 and 27% error, respectively, compared to the ideal gas law pressure. In all honesty, under normal conditions experienced in lab or on Earth, the ideal gas law would work fine. But under special conditions, van der Waals equation might work best.